It's okay. It's a good. Now it's good, huh? So okay. So I was told that the topic of my talk should be about quantum information. So I kind of decided to go with quantum information systems, and I have one introductory slide, which basically what generally this field is about. Is kind of a quest for controlling quantum world. And so in this quest, what we're trying to do is to isolate and control some simple quantum objects and then use them as building blocks to build more and more complex systems from them. And so what we would like to do with these systems is to study new physics, and usually it's a physics of engineered many-body systems, creating and probing new states of matter. But also, hopefully, we can start, exploring new applications such as quantum computing, quantum communication, and quantum metrology. So this is, as you know, without a doubt, is a very exciting field, and you can read about them almost daily in the newspapers. But this field, nevertheless, faces two big challenges. So one of them is a challenge of building truly large-scale quantum systems. And large-scale here might mean different things. It means just a large number of qubits, or it means, for example, scale of quantum network, how far we can, move entanglement around, how far we can separate entangled objects. So, and so that's actually, like, right now, I would say we don't know really the answer to this question, So, but even more strikingly, there is another question is, what can we do with this system? So, for example, like if I were to bring here a quantum computer, maybe you guys are sophisticated audience. If I gave it to you, would know what to do with that. But I mean, in truth, there are very few examples of really useful applications. No. And so, answering these questions, I would like to claim is a very exciting challenge. And it's both a scientific challenge and an engineering challenge. And basically, this interface between these kind of two fields involving science, engineering, and applications is, to me, what makes this field exciting. Now, this single slide is the only thing which I kind of, planned to show to begin with, and there comes a question. So I have in principle kind of two subjects I can talk about. So one is a subject involving kind of using kind of these ideas to try to build real-world quantum networks. And another one is to use these ideas to build quantum computers. You guys have a choice what you So in principle, initially I plan to talk about quantum computers, but I will talk about quantum computers tomorrow. So hypothetically, what I can do is I can actually tell you about some of the kind of ideas which goes on towards realization of quantum networks, and then maybe give a short introduction to quantum computers. Or I can have you vote. So who prefers quantum networks? Oh, look at this. Oh, man. Okay, wow. Okay, all right, okay, all right, okay. So, all right, okay. All right, so then I will proceed, with, and okay. So quantum networks deal with this subject of communicating quantum states. And this, in fact, historically was, one subject in particular involving the use of this quantum communication for quantum key distribution was one of the very first applications which people started to develop and even deploy in some sense. This already, this slide is, a few years old. It's kind of, it shows that, there are a wide variety of systems, and actually even kind of networks that have been developed. So, for example, this is a link between Beijing and Shanghai, but this link is not fully quantum. So it has this kind of intermediate nodes. They're called trusted nodes. So basically, the idea in this link is that you can send quantum states between these nodes, but then in these nodes you basically decode, you convert quantum information into classical and then you re-encode again and send it on. So this is not actually in many ways a real thing, because ideally what you would like to do, you would like to send quantum states without decoding them in the middle. In fact, ultimately you would like to use it to wire quantum computers together, to basically wire them in a single big network. But this actually in practice is challenging, and the reason is that any practical quantum channel has a photon loss, and basically this photon loss basically prevents sending the quantum states directly over long distances. So this kind of challenge has been recognized very early on, and particularly in this paper by many famous people, whom you of course know, kind of pointed out that there is actually a way to circumvent losses in quantum communication. And the idea of these so-called quantum repeaters is to essentially build a system where you have some kind of memory nodes where you can store quantum states, and then you basically entangle these nodes, these memory nodes, and then once you have some degree of entanglement, you can then use it as a kind of basis to, for example, purify these quantum states, or sometimes distill, higher entanglement. So how many of you know what is entanglement purification and entanglement distillation? You guys are sophisticated audience. So basically, the idea of this is that if you have multiple bell pairs which have some entanglement, but this entanglement is impure. So what you can do by making kind of joint measurements, by basically not measuring them individually, which would destroy entanglement, but making joint measurements on these multiple pairs, you can actually probabilistically purify them into higher entangled pairs. I mean, that's the idea of entanglement purification. So, so basically what this means is that these quantum repeaters, these are these little colored nodes here. They are small quantum processors which can be efficiently coupled to photons to receive the information sent in photons, and then you can actually use them to correct and errors in loss and also in some other quantum operations. So this research in quantum repeaters is by now basically almost 30 years old, 25 years old. And I can tell you that when I was starting, when I was still like a graduate student, when I was starting as a postdoc, some of us, and not just myself, but some other people, we thought that this quantum repeaters is maybe a first application of quantum computers. It's a nearest term, kind of application. And you will see where the field is in a couple of slides. Okay, so basically, in order to realize these quantum repeaters, one requirement is that you need to couple photons with these memory qubits, very efficiently. And there is a way to do it, and this way is called cavity quantum electrodynamics. So this one specific kind of approach, which we will be utilizing, will involve basically confining photons to very small volumes, and utilizing the fact that once photons are confined to very small volumes, if you bring, for example, a single emitter and nearby and couple these emitters to this small volume cavity, this coupling can be very large. So this is a version of something which is called cavity QED, which probably many of you have heard about. So who have heard about cavity QED? That's good. So, all right, so one way of doing cavity QED, as already mentioned, is to basically take the photons and confine them for the structure which is shown here. So what's shown here is this one-dimensional so-called photonic crystal cavity. So it's basically a dielectric wire which you perforate with these holes. And basically what these holes create, they create kind of a Bragg structure which you can reflect the photons which propagate into this wire. And basically, if you make one of the holes a little bit different, you can then confine these photons to this very small volume, which actually can be even smaller than the optical wavelength in principle. And again, these ideas are actually going back to almost 30 years ago, but it's up to very recently. It has been very challenging to couple, for example, single atoms or single emitters to this kind of cavity. And the reason is that, for example, like, you need to either trap single atoms, neutral atoms in the vicinity of such a structure, or you need to somehow create the solid state emitter inside this structure. Okay, to basically utilize this approach, we will be using in this part of the talk artificial atoms. So they basically will be like defects, impurities in solid state. So in this particular case, will be in diamond. And these are basically defects in a crystal, in diamond crystal, which in fact are the ones which bring color to diamond. So usually diamond is a colorless material. I might even have actually a sample here, but okay, it's, for show and tell. But but basically, if you, for example, bombard these crystals with some ions, you can create some defects inside, and they essentially behave like trapped atoms, for many purposes. And in particular, they are light emitters, and they can fluoresce, and this basically is what gives diamond this kind of this color. So the most famous impurity in diamond is the so-called nitrogen vacancy center. So probably at least some of you who work with NV centers here. So who works with NV centers? Just one person. See. So and they basically like the kind of this, the structure here is that you have a nitrogen atom which replaces a carbon atom, and there is a kind of kicked out carbon atom with vacancy. They form basically kind of, it's more like a molecule in this case, an atom, it's a molecular type center. And actually, you can kind of think about it as a trapped ion, in the sense that it has kind of optical properties, some, reasonably narrow emission line, and you can actually isolate these defects by using, for example, laser microscopy. So this is a picture of a reasonably pure diamond sample, and what you see here is basically these little dots, which kind of looks like a stars, are actually individual color center. So note that, in this case, it's a natural sample. They're kind of disordered, so you can try to kind of implant them. Also, you can create a, some array, and we can talk a little bit about, what are the issues here. So, but another important property is that they have a spin state in the ground. In the ground state, there is a non-zero electronic spin, and this spin degree of freedom can be optically polarized using like optical pumping techniques, and it can be also rotated with microwaves. And for this NV center, is actually what's remarkable is it actually displays millisecond coherence even under ambient condition and room temperature. So in many ways, this is actually a unique type of qubit, So you might ask, why don't we sort of build and sell room temperature solid state quantum computers using NV centers? So the reason is actually the following. So if you try creating this kind of NV centers on demand, what you see is that this kind of implantation process and the process of basically formation of this NV center is probabilistic. So this actually is relatively old picture, maybe more than 10 years old, but it's still kind of a state of the art. So you can basically create some arrays, but note that these arrays here, that is, NV centers are separated by 10 micrometers, so it's actually large separation, so they really don't talk to each other, they don't interact with each other. But even here, what you see is actually quite a bit of disorder. So, okay, so basically, and all of these things, basically show both challenges and opportunities. So on one hand, you can use as NV centers to create small quantum register, and in fact even perform small scale algorithm and do some error correction experiments. So actually they've been used for Bell test experiments where you can, entangle two NV centers separated by kilometers. And actually one maybe most practical use of them is for quantum sensing applications. But the real challenge is that there is a lot of disorder. Also, like if you look at optical transitions, they're actually inhomogeneously broadened and undergo things like spectral diffusion and many of, and this is especially if you confine them to small structures. So for this reason, this is still an active research direction, but kind of for practical systems, especially involving multiple NV center qubits, this actually is, it turns out their realization is challenging. So fortunately, NV center is not the only one defect. So there is actually other types of defects. In fact, by replacing the nitrogen atom with a silicon atom, it turns out that you can really change the properties of these emitters quite drastically. So in particular, what happens is that if you, for example, start with a silicon or germanium atom, they are kind of, physically just a little bit bigger than nitrogen atoms, so they don't fit on a given kind of lattice site. So as a result, what in this case happens is that you created a defect which is called interstitial. It kind of leaves this silicon ion kind of lives in between the two lattice sites, and it actually has very important consequences. So in particular, this silicon vacancy center, as opposed to nitrogen vacancy centers, do not have a permanent dipoles. So because of the symmetry reasons here, the basically permanent dipole for each eigenstate of silicon vacancy center will actually have to be 0. So there might be still transitions between the states, which are dipole allowed, but much like, for example, for hydrogen atom or rubidium atom in a free space, for each eigenstate, to the leading order, if you apply electric field, there is no shift. So it means that the dipole, permanent dipole moment is 0. So, and as a result, for example, what in these systems, what happens is that, like this vanishing dipole moment dramatically suppresses sensitivity to electric fields and this spectral diffusion. So basically remember that all of these atom-like systems, they are confined in the solid state objects. In the solid state objects there are a lot of things which are going around, so it's not vacuum, So, and in particular, like there are some various types of charges and so on, which typically create electric fields, and these electric fields shift lines and broaden transitions. And so basically, for example, the way how it shows is if you do spectroscopy, if you just take a reasonably pure diamond sample and just look at different silicon vacancy centers, what you find is that their lines are nearly on the top of each other, and this is opposite to NV centers where the lines are broadened by a factor of 100 or 1,000 typically. So basically what this really means is that this is a much more atom-like defect as opposed to NV centers, at least for kind of optics applications. And then what one could think about is basically, just taking one of these defects and creating it in some of the small kind of wires where you can hope to confine the photons. So this slide is a result of many years of blood and sweat, by many generations of students, and essentially what we kind of learned through this research is how to actually literally carve out small wires out of the diamond samples. So, and this is actually a technique which has been up to until very recently state of the art, and in fact this is a technique which is still used in the devices, which I will show. So where basically what you do, you basically through lithography, you kind of create this, kind of posts, and then undercut this post using, for example, Faraday cage by reactive ion etching. So the real pioneering work, on this area has been done by Birgit Hausmann, who is a native of Ismaning and a graduate of TU. So And she was a student of Marco Lankar at Harvard. And so basically using this approach, you can create devices with these unique optical and mechanical properties. And as I said, this is actually like, I think the first paper on this subject was by Birgit was like 2009 maybe, you know, so. And this actually has been now ongoing collaboration between my lab and a couple of other labs by Hung Kun Park and in particular Marco Lankar, who was, you know, with whom Birgit worked, and actually also Dirk Englund. So, okay, so with all of this, you know, the kinds of devices which we make are this of the type shown here. So what is actually shown here? So we have like these arrays of these diamond wires, basically with these holes. And, you know, this is actually zoom into one of them. And what you see is that there are these other, so actually we couple photons in and out using these tapered optical fibers, which we bring, you know, basically very close and to one of these devices to kind of basically suck photons out of this small wires. And, you know, there is all of this other infrastructure. So, for example, there's gold pads which kind of deliver, you know, microwaves and stuff like that. So when all of this is said and done, so here is how one of the structure looks like. And so basically this is like the region where we have this kind of nano cavity. So basically we create the silicon vacancy by implanting silicon ions in this cavity. So this implantation is actually not completely deterministic. So we basically need to then look through many of these devices one at a time. But you know, like if you find a good device, then and we interrogate it. So we need to somehow take the photons in and out of this device. And actually, the technique we use is all these tapered optical fibers. So what you do, you basically hit the fiber and pull it, you know, and basically pull it up to the point where it breaks. And what happens is that you can, using this technique, you can convert the mode from this small kind of sub-wavelength size waveguide into the fiber, and it can go to the kind of real world outside of the, in this case, a cryostat. I'll talk a little bit about it. So basically, when all of it is said and done, so we can have some systems which actually have very competitive cavity QED systems. So this, for example, is one case where you have one silicon vacancy which can be coupled to this mode. And actually, you can realize, using this approach, you can realize systems with cooperativity, which is, you know, kind of a measure of the single photon, single atom interaction, larger than 100, and with also very high coupling efficiency. You can kind of put the photons in and out with probability more than 90%. So it's actually many generations of students and postdocs kind of worked on this, and, you know, as I said, it's actually have been quite an adventure. So maybe let me just stop here and see if there are some questions. So actually, by the way, I would like to encourage questions during the lecture. So any questions?
Thank you. So you mentioned the millisecond coherence times before, but can you actually talk a little bit about typical timescales in the system in terms of interaction with the photons, Rabi frequencies, etc.?
So like what you see here, for example, is cooperativity. Okay, it now depends on which timescales, you know. So you're referring to, so cooperativity is basically the rate of enhancement of the coupling, of optical coupling to the cavity. And, you know, basically in particular with this enhancement, so the natural like decay rate, the natural line width, optical line width can be 100 megahertz. So this, you know, this thing can be like 10 gigahertz. So it can be very, very fast, you know. But this is just one type of interaction. So then like 1 millisecond referred to spin states. So to drive spin states, you need to drive microwaves, and it's, in principle, you can drive them very fast, but there are some practical limitations, but still this kind of this microwave Rabi frequencies can be easily, 10 to maybe 100 megahertz, But of course, what you would like to use, and I'll talk about it, eventually you would like to use nuclei as a memory. And of course, for nuclei, the lifetimes can be longer, can be seconds, but of course they are coupled much more weakly to magnetic fields, for example, to radio frequencies. So there, the radio frequencies can be, I don't know, tens of hundreds of kilohertz. So there is a kind of a spectrum, if you want, Yeah.
Because you say the dipole elements are actually vanishing for the silicon.
Well, right? Not the dipole, in eigenstates I'm mentioning, but there is an optically allowed transition. It's like an atom, like, hydrogen atom in each state. Dipole moment is 0, but there is a transition element between. Yeah.
More questions? Yep.
How do you attach the tapered optical fiber to the tapered
So, in these devices, which we are utilizing now, so basically what we do, we position this tapered fiber into the into stage, and we basically just, mechanically bring it in and just park it there. And so there's maybe some van der Waal attachment, so it's actually reasonably stable. So, but there is now an effort, to do a little bit more robust packaging. So it turns out that if you use certain type of glue, you can gently glue these things, even, yeah. And you have to do it in the right spot that doesn't, you don't want to expose your mold to this glue, but, yeah. Yeah, but these devices, we bring it in and just park it there, So, yeah.
Can you control how the silicon vacancy aligns with your cavity mode?
No, we cannot control it. So this is why there is a kind of, we can, of course, once we have these devices, we can characterize them, we can find out how they aligned, but this orientation, at least now, is probabilistic. So there are ways, my understanding is, at least for nitrogen vacancy centers, there are ways to create them in a right orientation preferentially by sort of proper, implantation and proper but I don't know if it's possible with silicon vacancy centers. Yeah.
So is there a set of specific orientation it can maintain, or?
Yes, there are some, there are there are just different types of, in a diamond lattice, yeah. Right? There are basically several sites, and that's how, okay. Yeah. So it's a deterministic set, Okay. Yeah.
Thanks.
Maybe a direct follow-up on that. What's the sort of efficiency to really get, let's say, the good cavities out of that? How many samples do you have to do?
Well, it kind of, so the typical. When we make these chips, right, we have, hundreds of these devices. One need to look through a few of them, but, typically on each given chip, we have, let's say, maybe dozens of, reasonably well working devices, but at least in terms of optical coupling, but then you want to make sure that they're oriented correctly, the spin coherence times, there is a variability, and I think this is actually one of the really limiting factors to this field. So in my second part of the talk, I will talk about neutral atoms, which do not have this property, So, and I think it's a big difference,
Thank you.
Yeah,
Fabian?
Thanks. Silicon vacancies have phonon sidebands, right?
They have, but it's quite weak, So compared to NV centers, where it's actually, this phonon sideband is very strong, I think here about 70% of the radiation goes in a zero phonon line.
Okay.
There is a little bit non-radiative recombination, but this is what's this is overwhelmed by this cooperativity.
Okay,
right?
so you do not see any perturbations to your resonance feature? in the upper left by the sidebands, or?
No, this, at this level there is
Okay.
really nothing. It's highly coherent, you know.
All right, thanks.
Yeah.
More questions? Otherwise,
Okay, so let me then just, you know, give a little bit of kind of examples of, you know, how we can use the system. And actually one thing I should kind of note is that the silicon vacancy and nitrogen vacancy center differ in several ways. So one of them, I mentioned that for nitrogen vacancy center, you could have a room temp, you know, a highly coherent spin transition at a room temperature. This is actually not the case for silicon vacancy centers. So, and the reason is that, you know, just in a kind of level structure, there is a spin orbit basically splitting. You know, there is a spin orbit state which can be excited through the phonons. And what it really means is that basically, you know, like if you prepare, for example, a spin state of silicon vacancy center and just at room temperature, you know, let it evolve, it actually will not have good coherence property precisely because, you know, the phonons can actually, you know, create this, you know, spin orbit sort of excited spin orbit state. So the price you have to pay for that, you have to cool them down. And the price for that is precisely about $500,000, you know? So I see, okay, good. And so basically what you need to do is you need to basically cool them to like temperatures, you know, below a Kelvin. And at that point, the spin coherence time become actually, you know, good. They become kind of milliseconds. And so that's the kind of device that you end up using. So, and at this point, you know, you can basically start kind of applying all of this kind of machinery, which, you know, you typically can use to, for example, you know, control qubits. So in particular, you can use this so-called decoupling, dynamical decoupling sequences. Do you guys know what it is? Do you know what spin echo is? So spin echo is basically if your qubit is subject to a random but static perturbation, by applying pi pulses, you can basically time reverse the evolution. So that's the idea of this dynamical decoupling. And so basically what you see here is that now you can recover this kind of millisecond you know, coherence time. So, and basically with this, you know, you can now start thinking about, you know, utilizing it as a kind of node of the quantum network. So first off, you have a reasonable quantum memory, you know, 10 milliseconds with electronic spins. So you can also use this coupling to cavity to, for example, read out and to initialize this spin state. And the idea is that, you know, basically these two peaks correspond to two spin states, and basically by just, you know, probing it at one of the resonance frequencies, what you see, you basically see this kind of like this histogram of counts, which actually can allow you to, for example, extract the fidelity of the readout, which actually is close to 4 nines, which is actually close to, I think, world record in any system. So you can also use now cavities to mediate interactions between two silicon vacancy. And in particular, you can also start using nearby nuclear spins to kind of encode information, and they can even have much longer coherence time. I will actually talk about it in a second. Okay, so here is one kind of example how one could use this system. And this is the example of the so-called heralded photon storage. So basically, you know, the idea is the following. Suppose you have an arbitrary photonic qubit which is encoded in time bin. So basically what you do, you create a state which is a superposition of an early arrival of the photon and a late arrival of the photon with some amplitudes. And you can do it by basically you know, sending your a single photon through the device which is called time delay interferometry. So basically you have two paths. One of them takes a little bit longer, another one is a little bit shorter, and basically, you know, you can, using this approach, create this type of photonic qubit. And then to kind of store this qubit in this heralded way, what you can do, you can basically reflect the photon from the cavity with one of the silicon vacancy centers, and you basically do it in the following way. So you basically tune this photon to a resonance with one of these spin states, and make sure that, you know, when photon arrives with this in resonance with the state space, it will get reflected. So at the same time, if you now prepared your qubit in another spin state, you know, then this photon will not get reflected. It will get, for example, transmitted in this case. And so basically you can then do this kind of storage information by doing the following. So you can initialize your spin in one of these, you know, for example, spin down state, then prepare a superposition of these two spin states, and then reflect the early component, apply the pi pulse, flip the qubit, and then reflect the later component. So basically what will happen in this case is that basically, you know, when the early photon is reflected, it will only reflect if the, your qubit is in a spin-up state. So it means that, for example, if initially you have a product state of the photon and spin, but this component will never get reflected. You know, and then you apply these piles and reflect a late component, and you also, using this, basically eliminate this other you know, part of this, you know, of this two-particle state, basically. And so what you see is that basically, you know, this just simple reflection using this kind of procedure creates this entangled spin photon state. Does it make sense? I see confused faces, you know. It's confusing? Okay. No? Okay. It's confusing. Okay, so we will do it again. So, all right. So initially you have this photonic qubit, right? And you have initially your spin state prepared in 50-50 superposition. So basically the initial state is completely unentangled. So this is just this product state, right? It's written, right? And then what you do, you basically utilize this spin-dependent reflection, and now we will be only looking at reflected photons. Everything else will not be, you know, will be thrown to trash. So in the early pulse, it will only get reflected if the photon in a spin-up state, right? So that's early. So this is early photon and spin-up. So this will get reflected, but this component, you know, if the early photon arrives early and the spin is down, you know, the photon will be transmitted. So that's why we can basically cross this part, right? And then what we do, we flip the atomic qubit, the spin qubit, right? We basically, you know, flip it, you know, and then basically we just, you know, kind of exchange up and down, and then the late one will basically undergoes the same procedure as an early, so it crosses, so this and this are crossed in the same kind of speed. So basically you end up in this spin photon entangled state. So basically what you can do now, you can use this type of operation to store the state of the photon in a heralded way. So basically just only when, if and only if you detect something, you know that photon arrived and it's stored without destroying a qubit. And the idea is the following. So this reflected photon, what you can do, you can basically measure it in the kind of X basis, in the basis which is a combination of early and late photons. So it's kind of a plus basis, plus minus. And so basically when you detect, for example, a plus state of photon, you know that your stored qubit is this. So and you see this, basically this beta early and beta late are imprinted now into this qubit. And likewise, if you know it's in a minus, it's actually the same state with just a minus sign. So this is kind of like, in a way, this is actually a teleportation procedure. So you entangle spin and photon, and then you measure the photon and teleport the state into the, and it's actually, this is a procedure which you can implement this, and it kind of works. In fact, it results in quite high fidelity, and with success probability, which is in this case is limited by how much photons you reflect versus how much photons are transmitted. So it's about 50%. So does it make sense? Yes.
How is this conditional reflection or transmission of the photon depending on the spin state achieved? Is it just by tuning the resonance of the cavity
Yeah, because this is, I kind of showed it here. So basically, because because the resonance of the cavity depends on which spin state you are, right? The spin states are split by magnetic field, right? And depending on which part, yeah.
And how do you tune the resonant frequency of your cavity?
We can tune it, and it's actually, and at least in these experiments, it's done by so-called gas tuning method. So what you do, you just put a little bit of the gas which condenses on this, and it can be tuned, the cavity, but these frequencies can be tuned by magnetic fields, right? So you can do both, Yeah. Yes. Yeah.
What kind of single photon source do you use?
So in this case, we use weak coherent state, right? And but this, because you have this heralding, it's okay, right? So it's only when photon arrives you detect it, but it will be, you'll see it will be a limitation, and yeah.
Physically, why would the state of a spin in the cavity change the cavity resonance frequency?
Because this because the frequency, the resonance frequency, depends on the spin state, right? Depending on which spin state you start, the frequency, this resonance will be different, right? So, if you want kind of a very deeply physical, is a spin-orbit interaction, right? Because spin mixes with orbital state, right? But so basically, so this is a level structure here, right? So there's a spin qubit, and you have, you excite the spin qubit into the kind of optically excited state, and what happens is that the splitting here is different from splitting here, right? Due to spin-orbit interaction, and that's why the resonance frequencies for two different spin states are different. So, okay, so this basic kind of primitive one can now utilize in many ways. And so the first example which I want to kind of illustrate it with is an example from 2 years, or actually more, 4 years ago now, is where we kind of used it to do something which we called memory-enhanced quantum communication. And so basically, in this experiment, it's a kind of a quantum key distribution experiment. And there is a version of quantum key distribution which is called measurement device independent. So basically, kind of the idea here is the following. So suppose Alice and Bob want to communicate with each other. And for example, they want to communicate to establish a secret key. So one way to do it is to actually place a beam splitter in the middle, and Alice and Bob can send photons, let's say single photons, in this kind of towards the middle station, and here in the middle, this beam splitter can actually be used to make a Bell state measurement. So if these photons arrive and you make a Bell state measurement, then fundamentally you don't know where the photon arrived from Alice or from Bob, and that you can use to basically like establish, for example, a secret key. So, and this actually approach is a basis for what's called measurement-based device-independent QKD. And so the question is, can you use this technique to actually, for example, increase the distance between this Alice and Bob? And as I already mentioned, when you increase the distance, the issue is that you start to increase losses. And what will happen in this case, is that, like if a distance is very large, then with high probability, at least one of these photons will be lost, right? And, if only one photon arrives, then basically clearly you cannot, these Alice and Bobs cannot, cannot communicate, So basically there is a way to kind of around it, and so basically as a result, for example, in this case, the probability of success will scale exponentially with distance due to loss. But there is a way around this, and the way is to put a device like ours which can actually store photons, photon states. So in this case, if Alice sends her photon and it arrives, and you know when it arrived, and you can store its state in the, for example, long-lived memory. So if the second photon arrives much later, you still can do Bell measurements on them, right? So basically, this memory allows you to do things asynchronously. And that's kind of a basic idea of these repeaters. And in fact, in this case, with just one repeater node, the success probability would still be exponential, but effectively you cut your length by 2 because the photon can arrive one at a time. That's kind of the idea. And so this is this kind of key is as asynchronous Bell measurement, and this is actually something which we implemented using this memory node. And in fact, what we have done is we basically kind of utilize the system to show that we can actually increase the rate. So so what in this graph, what we do, we actually plot this, kind of key rate, basically number of bits per channel use, which we create between these two nodes as a function of loss in the channel. And in this case, the losses were just kind of we artificially kind of introduced this loss by making fiber kind of longer. And what we see is that basically that this is the best possible direct transmission. This is like experimental, what's called sifted key, but this key has errors. And so if we then distill a secure key, even in this case, what we see is that basically this rate which we can achieve with this kind of heralded memory is larger than the best possible kind of classical rate. So I should say that, this experiment has a number of caveats, So one of them is that it's really kind of like is an artificial, it's a kind of a laboratory setting, so we do not, for example, use the kind of state-of-the-art fiber, so this loss is in a way artificially introduced. So basically the question is, how well this kind of things will perform in the real world. And this is what I kind of would like to turn to in the next maybe 10 minutes or so, right? So, to basically kind of, take this kind of very simple demonstration and make it into something which at least potentially could become practical. A few improvements are needed. So first off, we need to actually increase the memory lifetime. And this was achieved by using a nuclear spin. So for example, silicon has several isotopes, and one of them, silicon, is 29, which is actually a nuclear spin. And this basically the combination of electron and nuclear spin form this kind of 4-state system. It's basically 2 qubits. And so you can basically, using this nuclear state and using dynamical decoupling, you can store quantum information here up to several seconds. So in addition, what you can do, you can actually improve kind of robustness of this memory procedure. And in particular, you can use this silicon vacancy, which are highly strained. And what high strain can do, it can push this kind of spin-orbit interaction, can increase it. And so it becomes more tolerant to higher temperature. And so using this approach, for example, we can perform entangling gates up to about, I think, 1.5 Kelvin. It's an entangling gate of photon entangled with electron. But actually, we can even do better by entangling the photon directly with nuclear spin. And this is done by using this procedure, which is called the phone gate. So basically, in a phone gate, what you do, you implement a sequence where basically in between early and late arrival, you actually apply a couple of kind of conditional like C0 operations, basically between between electron and nucleus. And so in this case, electron should really not change its state at the end of this operation, so it just acts as a mediator. So what you do, you entangle electron and nucleus directly, and then you can do it up to 4 Kelvin. And one last thing which you can do is you can now utilize this electron degree of freedom as a kind of flag. So it's related to something that I will talk about tomorrow, about quantum error correction. So, so basically, note that, you know, ideally, if everything is perfect, you know, electron should start in a given state and should come out from this gate in a given state. But if an error occurred, the electron spin can be flipped. And so what you can do now, you can measure the electron state without disturbing either photon or nucleus, and then condition your kind of output, you know, on electron being in the right state. You know, so basically, if electron is in the wrong state, you just throw away this result. So it's a form of error detection. So it's not an error correction, it's an error detection procedure. And so, in fact, you know, you can see that, you know, basically, you can improve, you know, somewhat the fidelity of these operations, you know, and actually also improve a bit, you know, memory, memory time here. Okay, so you know, putting this kind of all together, so we have now started experiments where we utilize more than one node of the network. And so, in fact, in particular, so we built a second deal fridge, which actually is technically is just about 15 meters from the first one. But kind of importantly, now these fridges are connected through the fibers, and in fact, we can take this fiber out of our lab and even put it, you know, somewhere, you know, kind of let it wander around the city of Boston. And so basically, this is a kind of like a prototype of a two-node network where we basically have, you know, silicon vacancies in 2 of these devices. We utilize this photonic beam qubits, and the first thing we'll try to do is just connect these 2 devices directly. And you'd say, okay, so it's now this fiber is not too long; it's, you know, a few tens of meters, so it should be easy to do. But there is one problem. So despite of the fact that silicon vacancy, I told you, is much less susceptible to inhomogeneous broadening, it still is susceptible. So in particular, in the small devices, if we take 2 of these devices, you know, then what we see is that it actually still has some distribution, inhomogeneous distribution of the frequencies. And so to kind of bridge it, and this distribution is in a kind of range of, you know, tens of gigahertz. So to bridge this distribution, what we do is we actually use frequency conversion. We frequency shift these single photons. So this frequency shifting can be done either directly using electro-optic modulation, or it can be done by actually converting this photon into a telecom frequency. And, you know, whereas if these 2 fridges are close to each other, we will use this technique. You know, if we want to send this photon into this telecom network, we will actually use this technique. So, okay, so first starting with this, you know, so basically what we do is we do the same procedure which I described, but now apply it to 2 nodes sequentially. So we start with the time beam photon, do this electron photon gate with a node A, then this, you know, photon goes to the node B, and then we do it with the node B, and then finally what we do is we measure the photon state, you know, on an X basis, and that creates an entangled state, right? And depending on which, whether we measure plus or minus, we'll create one or the other Bell state. And so in this case, then what we can do Bell state tomography, and basically what it really shows is that we indeed have, you know, 2 entangled spins now in different cavities. So it's actually interestingly, depending on which state you measure, the fidelity is different, and we can talk a little bit about it, because it turns out that different, you know, these 2 different Bell states are differently sensitive to errors. But you know, and actually these, and all of these inefficiencies are taken into account, despite of the fact that we have high coupling rates. Our, you know, rate is actually kind of is at most 1 hertz. And in fact, most of the time is actually, if you want high fidelity, the rate is actually even smaller. And this is in part due to the fact that we still use coherent states, we use weak coherent states. So basically, if you start with stronger coherent state, you have a higher rate, but you have worse fidelity. So, okay, so we can then now utilize all of this machinery which we developed and also create nuclear entangled states. So in this case, what we do is we start with this photon and then perform this phone gate on the first node, then perform the phone gate on the second node, and then measure the photon and then apply this dynamical decoupling. And moreover, we can now use this error detection on both. We look checking both of these electron spins, right? If both of them are in the right state, fidelity will be higher, should be higher. And indeed, this is actually the case. So basically, these two plots, so one of them, utilizes, I think the upper one utilizes error detection, and another one does not. So what you see is that we clearly see that kind of, that fidelity, can be, or Bell state can live for a longer time if you utilize error detection. Okay, so putting this all together now, so what we can do is we can try to extend the range, and there, what we do is instead of this just electro-optic modulator, we put this frequency converter which down convert the photon after first interaction into this telecom O-band, and then eventually up converted before the second interaction. And basically, this, allows one to travel through either spools of the low loss fiber or go into real world kind of network. And so the kind of, so this frequency conversion is actually kind of a remarkable process because it allows you to basically shift the frequency of the single photon anywhere. And it's actually, these things are already getting pretty good. So in this case, we have about 30% conversion efficiency and this 2.5 hertz measurement noise counts. Both are important characteristics. Okay, so putting this all together, what we have done then is to take these single photons and kind of move them outside of the labs. So this is, like two nodes which are 20 meters away from each other. But what we can do, we can take these single photons and put them into this fiber, which actually goes, so it's a Boston map, so it actually crosses Charles River. In fact, it crosses this fiber, it's a loop, which kind of travels in one direction and then travels in the other direction. It crosses Charles River 6 times. And, at the end of the day, actually, this channel has over 17 dB loss, which actually is much more than like than normally that fiber would happen. The reason is it goes through a couple of switching stations, so each of this switch adds the loss and so on. So basically, okay, so with that, we can, basically, have to measure for a long time because the data rate is not very high, but, we obtain still that we have an entangled state, and this entangled state has fidelity, which is above the threshold for the Bell inequality, and basically that way we can really do heralded entanglement of two multi-qubit networks across metropolitan scale deployed fiber. Okay, so that's actually kind of a very new paper which appears this week, so maybe it's not appropriate for the summer school, but hopefully it gives you a little bit of feeling, where the frontier is. So as an outlook, what do we want to do with this kind of system? So first off, you can utilize already it as a kind of to do proof of concept experiments to do something which is called blind quantum computing. So blind quantum computing is the mode of quantum computing where you basically send commands to the quantum computer in such a way that no one, including the owner of quantum computer, can even theoretically find out what type of computation you can do. So you can also use this approach to do non-local quantum interferometry by basically having sort of two receiver nodes, for example, in a telescope, which can then sort of use teleportation to basically, do like this interferometry over a long baseline. And finally, because we are using this frequency conversion, we can now also think about networking for dissimilar systems. Okay, so that ends actually normally the first part of my lecture, but I would like to thank you for your attention. This is kind of an amazing Silicon Vacancy team and some of our collaborators, so thank you very much.
All right, I know if I turn around, I will see some scared faces from the group leaders that I picked beforehand. We will anyway go into these groups and try to answer the few first questions just within that group. So I'm going to put up the list again.
Okay.
Reasoning like most of the people that I